Now that we introduced the one-to-one linear transformations, we are interested in defining onto or surjective linear transformations. Let T from V to W be a linear transformation. And suppose W is a finite dimensional set. Then T is onto if and only if the rank of T is equal to the dimension of W. So as long as the range and codomain are the same, we're going to say that, hey, we have an onto linear transformation. So the rank of T must be equal to the dimension of W. Theorem, one-to-one and onto linear transformations. Let T from V to W be a linear transformation with vector spaces V and W, both of dimension n. Then T is one-to-one if and only if it is onto. So as long as V and W have the same dimension, if T is one-to-one, for sure you can say that T is onto. If T is onto, for sure you can say that T is one-to-one as well. So let's take a look at the proof. If T is one-to-one, remember that the kernel is equal to 0. So the dimension of the kernel of T must be equal to 0 by definition. In this case, the dimension of the range of T, as you remember, is n minus the dimension of kernel T or the nullity of T, which is n, because this guy is just 0. So you just showed that the dimension of the range of T is the same as the dimension of W, which is n. So T is onto by definition. Similarly, if T is onto, then the dimension of range of T is equal to the dimension of W, which is n. Well, what's the meaning of that? It means that the dimension of kernel of T must be equal to 0. It doesn't have any other choice. N on the other side, on the left-hand side, and n on the right-hand side. So when the dimension of the kernel is equal to 0, it means that T is a one-to-one linear transformation. Consider the linear transformation T that maps n space to m space. It's represented by Tx equals to Ax. Question says find the nullity rank of T and determine if T is one-to-one, onto, or neither. You have a 3x3 matrix. So what are we going to do? We're going to analyze each matrix. So this is our very first matrix. The pivot is 1, everything below 1 is 0. Here you have 1, below 1 is 0, and then you have 1 here. So you don't have to write it in reduced form. You're going to list the linear transformation, the dimension of the domain, the dimension of the range or rank of T, the dimension of kernel or nullity of T. Is it one-to-one or is it onto? For the very first one, since it's a 3x3 matrix, it means that it maps the space to itself. So the dimension of the domain is equal to 3. There is no doubt there. It's easy to see that. What is the dimension of the rank? What's the dimension of the range or rank? It is also 3. Well, what is the dimension of the kernel or nullity? It must be 0. It doesn't have any choice because n is equal to 3 plus 0. It cannot be any other number. Is it one-to-one? Yes. Why is that? Because the dimension of the kernel or the nullity is equal to 0. Is it onto? Yes. Why is that? Because the dimension of the range or the rank of T is the same as the dimension of the W here. So this is your V, everybody, and this is your W. W is of dimension 3, the same as the dimension of the range, which is 3. The second matrix, here you have a 3 by 2 matrix. So if you want to represent a linear transformation, it maps R2 to R3, everybody. So take a look at V. The domain is the plane, and the range is your space, or specifically the codomain is the space. So what's the dimension of the domain? It is 2. What's the dimension of the range? The dimension of the range is 2. What is the nullity? The nullity is 0. Take a look. Nullity doesn't have any other choice. It is 2 plus a number. That number must be equal to 0. Is this 1-to-1? Yes, of course. Why is that? Because the nullity is equal to 0. The dimension of the kernel is 0. Is this onto? No, it is not onto. Why is that? Because the dimension of the range is equal to 2. It's not the same as the dimension of your W. They are different. This is 2 and this is 3. They are not equal to each other. So there is no way T is onto. Let's take a look at the third matrix. This matrix has 2 rows and 3 columns. So 2 by 3. Now, if we look at the linear transformation maps R3 to R2. So we are reducing the dimension from the space to the plane. Well, the dimension of the domain, as you can see, is 3. The dimension of the range is equal to 2. The nullity is equal to 1, everybody. 2 plus 1 gives you 3. Since the nullity is not 0, it is not 1-to-1. But is it onto? Yes. Why is that? Because the dimension of the W is 2, and the dimension of the range is also 2. So since these two numbers are the same, you're going to say that it is onto. And finally, take a look at this 3 by 3 matrix. This matrix maps the space to the space itself. What is the dimension of the domain? It is obviously 3. You have 2 non-zero rows. So the dimension of the range or rank of T is equal to 2. You can easily calculate the nullity, which becomes 1. 2 plus 1 must be equals to 3. Is this 1-to-1? No, of course not, because this guy is not 0. Is this onto? Of course not, because 2 is not the same as 3. So the dimension of the range is different from the dimension of W. So I gave you 4 different examples so you can analyze different types of linear transformations using their matrices.